When we design certain circuits, sometimes we require capacitors of a particular capacitance which may not be available in the market. So we have to combine the available capacitors to obtain the desired value. So in such cases, we have to make combinations of capacitors. We can connect capacitors in two different ways. The first is called series combination and the second one is called parallel combination. In the first figure, you can see three capacitors which are connected in series. So the capacitors are connected one after the other and they are connected to a power supply. So when we do connection like this or in series combination, the potential difference across the three capacitors will be different, but they will store the same charge in them. That is, the charge stored in three capacitors will be Q, but the potential across the first one will be V1, second one will be V2, and the third one will be V3. Now in parallel combination, actually what we are doing is we will connect the first three plates together to a common point, then the next three plates to another common point, and the power supply is connected across them. So when you connect them in parallel, the PD across the first, the second and the third will be the same, but they will store different charges Q1, Q2 and Q3. Now let us discuss in detail the series combination. Consider three capacitors C1, C2 and C3 connected in series and a voltage of V is applied across the combination. The capacitors, when we connect them in series, the charges in all the three capacitors will be same and it is marked as Q. But the applied potential difference V is divided into three. V1 across the first, V2 across the second and V3 across the third. So this potential difference is shared between the three capacitors. Or in other words, if I want to move a unit positive charge from here to here, the total work done is V. I can do that action in three different steps. First, I can bring that unit positive charge from here to here across C1. For that, I have to perform a work of V1. Then I can bring it from here to here. The work needed is V2. Then I can move it from this point to here and the work done is V3. So the total work done or the total potential difference V is equal to V1 plus V2 plus V3. And now we can calculate the values of V1, V2 and V3 from the basic equation of capacitor. C1 is equal to Q by V1. Therefore, V1 is equal to Q by C1. V2 is equal to Q by C2 and V3 is equal to Q by C3. And V is equal to Q by C1 plus Q by C2 plus Q by C3. Or it can be written as V is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now we can define the effective capacitor of series combination. So the effective capacitor means a single capacitor which can perform the work which was done by all the other three component capacitors. Now what they have done, those three capacitors together stored a total charge of Q at a potential V. Now if we have a single capacitor whose capacitance is Cs, and when I apply a potential difference of V across it, and if it is able to store a charge Q in it, then I can call the Cs as the effective capacitor of the combination of the three. Or this capacitor effectively replaces the combination. So in this situation, I can say V is equal to Q divided by Cs. So in the last part, we have seen another equation, that is V is equal to Q by C1 plus Q by C2 plus Q by C3, or Q into 1 by C1 plus 1 by C2 plus 1 by C3. So we can equate those two potentials so that Q by Cs is equal to Q into 1 by C1 plus 1 by C2 plus 1 by C3. Comparing these two, we can say 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now we can discuss the series combination of n capacitors. So if n capacitors C1, C2, C3, etc. Cn are connected in series, the effective capacitance of the combination is given by 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus etc. 1 by Cn. Now if all these C1, C2, C3, Cn etc. are equal to C, or all of them are identical, or if you connect n identical capacitors in series, the effective resistance is given by Cs is equal to C by n, or 1 by Cs is n by C. From that we can conclude Cs is equal to C by n. Okay, now we can go to parallel combination. So consider the parallel combination of three capacitors C1, C2 and C3. The charges stored in these three capacitors will be Q1, Q2 and Q3. But the potential across these three capacitors remain same as V. Okay, so the charge which is stored in the first, that is Q1, in the second, that is Q2, and the third in Q3 are all drawn from the same source. So the total charge which is drawn from the source, or the total charge stored in these three capacitors, is given by Q is equal to sum of the Q1, Q2 and Q3. So this is written as equation number 1. Q is equal to Q1 plus Q2 plus Q3. But we know Q1 is equal to C1 into V, and Q2 is equal to C2 into V, and Q3 is equal to C3 into V. Or Q is equal to C1V plus C2V plus C3V, or Q is equal to C1 plus C2 plus C3 into V. Again, I am introducing the effective capacitor, which is effectively replacing the combination, and let that capacitor has a capacitance of Cp, or when I apply a potential V across it, it is able to store a total charge Q in it. Then only we can call it as the effective or equivalent capacitor. For such a capacitor connected to a source of voltage V, Q will be equal to Cp into V. Comparing this equation with the previous one, you will get Cp into V is equal to C1 plus C2 plus C3 into V, or Cp is equal to C1 plus C2 plus C3. Or in parallel combination, the effective capacitance is the sum of all the individual capacitors. Now I can discuss the parallel combination of n capacitors. We have n capacitors of capacitance of C1, C2, C3, etc. Cn, and if they are connected in parallel, Cp will be equal to C1 plus C2 plus C3 plus etc. plus Cn. Now if all these are identical capacitors of capacitance C, then Cp will be equal to C plus C plus C plus C n times, which is equal to n into C. So the effective capacitance in parallel combination will be higher than the capacitance of all the individual capacitors. But in parallel combination, but in series combination, the effective capacitance will be less than the individual capacitors. We have to consider the minimum component capacitor, not its capacitance. The effective capacitance will be less than the least capacitor which was used in the circuit.